Question 6. Compound A is a halogen alkane. Name compound A. So we've got 1, 2, 3 chloro. We've got a 2 methyl and a 4 methyl. Okay, so it's actually going to be slightly tricky. It's going to be 3 chloro dash 2, 4 dash di, because there's 2 of them, 2, 4 di. What is it? It's a methyl. And what's the longest carbon chain? 5. So it's pentane. Pretty hard one. 3 chloro 2, 4 methyl pentane. Dimethyl pentane. Then it says, drawn figure 3 in peaks of the main molecular ions in mass spectrum of A. So we know that 75% is 35Cl, and therefore 25% is going to be the rest. So what we're going to want is, well, each bar represents 25%. So 134 at 75%, and then 136 at 25%, and that will give us a total of 100%. Reaction of A with warm dilute aqueous sodium hydroxide. Nucleophilic substitution. Because how do I know? Sodium hydroxide will form an alcohol. Yeah, that's obviously going to be nucleophilic substitution. So what happens? Well, the OH minus, one pairs of electrons, and the OH minus. Well, what do we have? Okay, there's a chloro, there's a partial positive carbon. Attack the partial positive carbon. CCl bond breaks. And now what happens is, it says include the structure of the alcohol B. Okay, is that this chlorine leaves and is replaced with the OH. So CH3 CH3 wants a full structure H CH, and where that chlorine is, instead of that chlorine, we've just replaced it for the OH. It's that simple. OH and then the CH, the CH3 and the other CH3 and another CH3. And I also like to then show that the chlorine has left with a negative charge and still has a lone pair of electrons, but it's not necessary. Pretty simple mechanism. 6.4, another mechanism one, but this time it's with hot ethanolic potassium hydroxide. This is the key thing. Dissolving ethanol, and it also gives an alkene. Well, it's going to be elimination mechanism. And the roles of our hydroxide ions in this case is they act as a base. So that's 2 marks. Now 4 marks for this. So we still have the OH minus with lone pair of electrons, but in this case what's going to happen is that it's going to take a hydrogen, take a proton. So it's going to go like here. Now the left carbon has a spare electron, so it wants to reform the double bond. It wants to form a double bond. In order to form the double bond, the CCl bond must break. Chlorine's partially negative, carbon's partially positive. Hopefully you can see, but that's just a curly arrow to the chlorine. And it's that simple. That's simple. Just learn the mechanism where the curly arrows go. Now what we're forming is not going to be that simple. This is going to be slightly hard. More difficult than this. Well, what happened? We've taken a proton, so the OH minus is going to become H2O. The chlorine's left, and we've got a double bond. So all that's going to happen is that this is becoming the double bond. So this C double bond C, and then your C, and your C. This becomes a double bond. That's what the curly arrow to the bond meant, reforming a double bond. The H. You still have the CH3 here. However, this hydrogen now, that was originally here, has gone. It's bonded with the OH minus to form H2O. This chlorine has also gone. So all that happens is we draw the rest remaining of the structure without that H and without that chlorine. So it should look something like that. And it could also show then plus H2O plus Cl minus. But it's not necessary again. And then 6.5, tick the box that shows the correct compound. It's either an alcohol or an alkene. Classic question. With the infrared spectrum, obviously we don't care about the less than 1500 centimeters to power minus 1. That's infrared fingerprint region. We don't care about that. So because it has a peak, here. Which one is it going to be? It's definitely going to be C, because that is around about 1620 to 1680, and that's where the peak is, and that represents a C double bond C. Alcohol can't have a C double bond C, so C double bond C as 1620 to 1680 centimeters to power minus 1, and that's the wave number. Or you could say that because there's a 30 to 35, 50, yeah, not really, but you could say it be here, and therefore it hasn't. No, since there's no 32, 30 to 35, 50 peak, therefore there's no OH group, therefore must be an alkene. And then 6.6, explain why D reacts more quickly than A with dilute aqueous sodium hydroxide at the same temperature. So D, compound D, CBr, compound A, CCl. That's the only really difference. Once I've spotted that, well, I should know that the CBr has a lower bond enthalpy than CCl. That's it. And then you could say, therefore, the CBr bond breaks easily, therefore faster substitution, therefore A reacts more quickly. And that is the end of question 6.